Hi everyone, and welcome to today's live webcast in association with Broadcom. This webcast will look at Broadcom's industrial time-of-flight sensor solutions, how they work, and how they could help you solve your sensing problems. Following an introduction to the working principle, our expert speakers will present the technology, which has been specifically developed for industrial applications with a need for speed, accuracy, small size, and reliable distance readings. You'll also learn how Broadcom's sophisticated ambient light suppression techniques enable the use of its sensors in outside environments, and how the sensors can produce reliable measurements against white, black, and coloured target surfaces, as well as metallic and retroreflective surfaces. To conclude, you'll also find out about some of the typical applications and use cases, and how the sensors can be applied to solving specific and real-world problems. I'm Keely Portway, and I'll be your moderator today, and I'm very delighted to introduce our expert speakers, Stefan Brunner, Business Development Manager, Time-of-Flight Sensors and Silicon Photo Multipliers at Broadcom, and Volker Goetzfried, Application Engineer at Broadcom. Just a bit of housekeeping in terms of format. We'll have a presentation from the guys, followed by a short Q&A session. If you want to send your questions in as you think of them, you don't need to wait until the end, and we'll read them out. So without further ado, let's get started. Stefan and Volker, the floor is yours.
Thank you very much, Keely, for this nice introduction. So as you said, we are talking today and present today our industrial time-of-flight sensor solutions. My name is Stefan Brunner, and here next to me is Volker Goetzfried.
Hi, everybody.
Before we start, just a short overview about our division's optical sensor product portfolio. So AFBD is actually the name of our product division within Broadcom. We have silicon photomultipliers, blue sensitive and NIR sensitive silicon photomultipliers. We have optical spectrometers ranging from about 200 nanometers up to 1700 nanometers, and we have pyroelectric sensors, which are sensitive up to 20 micrometers. Today we are talking about our time-of-flight integrated sensor solution, which are based on APD. And here we're working with 680 nanometers and 850 nanometers lasers. Before we get into the topic, just a short overview about the distance measurement methods. There are many different methods to measure the distances. Here I showed a use case of why we would like to measure distances. This is a typical warehouse situation where a forklift is actually working together with people in the warehouse. And of course, you want to avoid injuries and accidents, and that's the reason why more and more sensors are integrated in those kinds of forklifts, for example, in order to prevent injuries and also damage to people and goods. And the methods to measure distances are manifold. So, for example, you could measure the distances by triangulation. For example, by projection of reflected light onto a sensor, a CCD line array, or you could use a dot projector onto an object. But you could also use stereo cameras. This is the parallax method, where you take two images of a scenery, compare them, and actually get a depth image. Or you can use the time-of-flight method, the TOF method. It's based on an echo, and in order to get an echo, you also need to transmit a signal, and the signal can be either, for example, acoustic, so it's an ultrasound sensor, or it can be electromagnetic waves like radar, or it can be optical like LiDAR. So we are today talking about this optical time-of-flight or LiDAR sensor methods for measuring the distances. So going here a bit deeper into the topic, there are two main methods of measuring the distances using light. Both can be named as LiDAR. There's first of all, on the left-hand side, the direct time-of-flight method. Here, for example, a very short light pulse in the duration of below 5 nanoseconds is emitted from a laser, for example, You see here the pulse shape. This is targeted onto an object, reflected by an object, and then also detected by a photodetector. And when knowing the speed of light and you're comparing when you have emitted the light pulse and you detect the light pulse, you can calculate the distance to the object. This sounds very easy. In practical, it's a bit more difficult than that. But on the other hand side, there is also an additional method, the indirect time-of-flight method, also continuous wave time-of-flight method, or the correlation time-of-flight method. So there are many names for the same. Here in this presentation, we call it indirect TOF or iTOF. The difference to the direct TOF is actually that here a continuously modulated wave or light is emitted from the laser or light source. You see it here in these square shapes, but it can be also a sinus curve, for example, is continuously emitted and modulated onto the object, and the reflected wave or pulse train is detected at the photodetector. And what's done then in the electronics, actually, the phase shift of the emitted pulse train and the detected pulse train are being compared and calculated, and out of the phase shift, you see it here, the delta phi, the distance can be calculated. Of course, there are advantages and disadvantages or challenges for both methods. So for the direct time of flight, actually, they can be very fast for single shots. So we were talking about these 5 nanoseconds pulse shapes. They can be very precise, but only if multiple pulses are emitted and detected by the sensor. And actually, there is a very large unambiguous range. This is actually dependent on the pulse rate. So just considering the pulses being emitted within 1 microsecond, you get actually a long distance which can be detected without any unambiguity. The challenges here are ambient light. So very often for direct TOF, silicon photomultiplier or SPADs are being used. They're excellent in detecting single photons and these very short light pulses, so they can be very accurate, very precise, and are good for long-range lidars. But with ambient light, they usually have a degradation in the range of these sensors. So this is a challenge in the optical design for the customers. And the overall system integration is complex because of this high-end electronics, which is needed for the laser drivers and also the photodetectors. In comparison to that, for the indirect time-of-flight method, the advantages here is actually the high ambient light immunity. So this also works very well in bright sunlight. There is actually a comparably low system complexity, and this is very noisy. This method is very robust, in noisy environments. So again, in very high ambient light situations like sunlight, but also if you have many LiDAR systems in the same floor, for example, in the same room, then this is actually a very robust method to be used. The challenges here are actually there's a trade-off of the unambiguous range versus precision. So the unambiguous range can be reduced and the precision can be improved, while it also works, of course, in the other way around. So there's a trade-off between those two parameters. And there's also a limited detection of semi-transparent targets. So, for example, if you would like to measure on glass surfaces and you would also like to detect the object behind the glass window, then it can be a challenge with the indirect time-of-flight module. So for both methods, Broadcom offers here the perfect and optimum sensor solutions. First of all, for the direct time-of-flight, we are offering the Broadcom's near-infrared silicon photomultipliers. You find them on our website. Today, we will focus actually on our integrated indirect time-of-flight module. You see it here in the picture. This is what we will now have a closer look to. Okay, so let's see the AFBR-S50. This is actually the part number of this product family. Is a high-end, fully integrated sensor module, and it measures the distance, as said before, using the indirect time-of-flight module. We designed here this time-of-flight ASIC, which you can see here. It has actually a 32 APD pixel array implemented. It also has integrated the complete APD front end, control, and also readout. And also integrated on the same chip is actually a reference pixel where we can measure the status of the laser, and we also have here integrated a laser driver. This IC is actually mounted onto a PCB. You see it here on the right-hand side in green. And we also have added the optics and the cap and the optics to have a fully integrated sensor module to be offered to our customers. You see here actually beneath the small lens, here on the right-hand picture, there we have a VCSEL laser, either at 850 nanometers or at 680 nanometers, while beneath the larger lens we have the receiver, meaning the 32 APD pixel array. Altogether, it looks big, but it's very, very small. We have here a very compact form factor of 8 times 12 times 12 millimeters, including the pins. Without the pins, we have here a height of 8 millimeters. And with this very compact and lightweight module, we're achieving actually a range spanning from 2 centimeters and goes up to 50 meters of range and even beyond. I will come to that in a second. We have up to 200 meters unambiguous range. It's all solid state, so we don't have any moving parts in this module. As said before, we have the laser light source integrated, and this laser light source is laser class 1, which is TÜV certified. We have excellent ambient light suppression of up to 100 kilolux and beyond. We'll talk about this in a second. We have less than 100 milliwatt power consumption, can go up to 3 kilohertz frame rate, so can have very high frame rates. And all that's needed there to work with this sensor is a 5-volt power supply and an SPI interface. So when looking here on the right-hand side on the graph, you see here on the y-axis the typical range for one of our products versus the ambient light. 1 kilolux is a typical indoor modern office situation, while 100 kilolux is bright sunlight onto the target. And you see here indoors for a 90% remission target, we achieve here 78 meters at 25 hertz frame rate. And this range is actually reduced by higher ambient light, but still we achieve here up to 22 meters of range in bright sunlight. While for black targets, we start at around 22 meters, and in bright sunlight, we're still able to see up to 10 meters with this tiny laser class 1 sensor module. Regarding our product variants, our products are all based on the same IC. So all of these sensors are coming with the 32 pixel APD array, but they mainly differ actually in the field of view of the laser. So we have variants with very narrow field of view, starting from 0.4 degrees times 0.4 degrees, where we illuminate just a single pixel on the sensor array. So you only get one distance reading, but a very focused view onto the scenery. We have then here our long-range variants with an opening angle of field of view of 2 degree times 2 degree. Also here we just illuminate 1 pixel, so you get 1 distance reading. This goes up to 50 meters and beyond. And we have here actually also our large field of view variants, which are mostly used in robotics applications. They can make use of the whole 32 APD pixel array, meaning you get 32 independent distance readings. And the field of view here is 13 degrees times 6 degrees. We're also offering here an extended range version, which goes up to 8 meters. Sorry, what is a bit unique here is actually that we have one variant, the one variant with the 0.4 degree field of view, because this is the only version which is working in the visible range at 680 nanometers, while all the other variants, they're working in the near infrared at 850 nanometers. And all this is shown here actually in our product overview. You see here the typical ranges, what we are talking about before, for the largest field of view variants, 5 and 8 meters. We have here actually one sensor in between with 10 meters and can go up to 50 meters and beyond. And one very special sensor is, as said before, the 680 nanometer sensor with the smallest field of view. With this one, actually, we achieve ranges up to 100 meters, for example, onto a retroreflector target. And we will talk about where to use this very good performance. You see it also in the table, the typical ranges or the ranges we achieve on white targets at 1 kilolux, so indoor environment at 100 kilolux, which is ranging from about 3 meters up to 78 meters. Regarding the accuracy, what we're achieving, so the typical accuracy is ranging from about 1% for this 85G variant, and is going up to about 2% accuracy for this extended range large field of view sensor. We have here actually different applications for the different sensors, so they optimized for the different use cases. Well, and this brings me actually to a slide with an application overview before I hand over to Volker. Our focus with these high-end sensors is actually on industrial applications where our customers need reliable distance readings, reliable and robust performance for example, for factory and industrial use cases. We will talk about field level measurements, about predictive maintenance in elevators. We will talk about stereo cameras. We talk about logistics robots like AGVs, AMRs, talking here also about cliff and void detection, and also functional safety with forklifts. Factory automation is a very hot topic, and also one use case where we are very unique and we have very good performance, actually the drone applications, which are depicted here below. Well, before talking too much about these applications, I will hand over to my colleague Volker. He's the application engineer, and he will deep dive with you into the specific and individual applications.
All right, so thanks a lot, Stefan. So as you mentioned, let us dive a little bit more into the specifics of the application. So one of the biggest fields which we see here is the fields of the logistics and factory automations. And more specific are the autonomous mobile robots and automatic guided vehicles, AMRs and AGVs. Those are the buzzwords for those specific application fields. So let us first, there is something in the slides, but doesn't matter. Let us go into the principal structure of an AMR, so which is depicted here in this slide. So usually on top you have a kind of a load. What is shown here is actually a Europalette from the side. So let us take this as a load for this AGV. And on the front side of an AGV, usually have the sensing peripherals like any sensors, a camera, or LiDARs. So the purpose of this peripherals usually is navigation or SLAM, obstacle detection and collision avoidance, in order to let these vehicles drive autonomously. So let us go a little bit deeper into the differences between the different sensing peripherals. So as mentioned before, LiDARs and stereo cameras are most often used as navigation tools. So they offer usually a really large field of view as well as a good resolution, together with a reasonable range of many meters, which is actually good enough for warehouse navigation. But on the other side, they also come along with a high cost. So single sensor source, or let's say the drawback here that a single sensor source, if you want to call a LiDAR and stereo cameras like that, they often yield or can yield into misinterpretations because it's just a single module which is implemented in one spot at the AMR. And these misinterpretations may then lead into a false data. So, and in the worst case, it may lead to injuries of the staff in these premises where these AMRs are driving in. So a reliable information of these sensor tools or of these devices is key to save really to save and stable to have a safe and stable performance. So in the end, also having not reliable information is also adding some additional money. So you really can save costs when you have a reliable sensing tool on those devices. This immediately translates when you think of a lot of AGVs times 100 driving around doing the job in warehouses. And they are not equipped with good sensor peripherals. And you see these issues, or you have these issues of misinterpretations, which either adds in some delays in the navigation or even some injuries, and the whole logistic premise has to stop its work. So therefore, really one solution or the solution which helps here is really sensor fusion, so to have redundancy in those systems. And yeah, this is then where specifically these small TOF sensors, which Stefan gave you a good introduction in, which Broadcom offers, may come into game. So going deeper into the use cases of typical AMRs driving around in these logistical premises. So the first one is from top to bottom is the so-called overhang detection. So if you think that of the cargo which is loaded onto the AMR, and you can think of pallet trucks which are also driving around in these facilities. They are loaded with some heavy loads at a certain height and driving around and then suddenly crushing into the cargo of an AMR, which is at the same height. So an AMR would need to detect actually the metal forks of such forklifts coming towards them. And this is the use case of the overhang detection. So this requires, of course, as can be seen here in all the three different use cases, in every case, a reliable detection for safety reason is required. It also requires, coming back to the overhang detection, really the detection of small targets. And what we have seen here is that 3D point projectors as well as stereo cameras are really showing here a poor performance, and this is even, or let us say for TOF cameras, this is the range is sometimes even not sufficient at all, and this is where the TOF sensors with the narrow field of use are really beneficial here. So second use case is the collision avoidance. If you think of collaborative bots which are working together with the staff in warehouses, they should not collide with them and cause some harm of humans. Therefore, this is also key to avoid that. just looking a little bit at the time. The last one is the cliff and void or stair detection. So this is also quite important, not to destroy the AMRs itself, so that the AMR can properly detect such dangerous situations and not driving down the stairs. So a detection sensor for that is definitely a field for the TOF sensor, which we are introducing to you today. So on this slide, there is a typical performance example. As you can see now in the picture, it's a live video. The TOF sensors are looking downwards the cliff. The robot is moving on a small platform. And when you look at the left picture, the white dots are detecting really the cliff, while the red dots, which is the LiDAR, a 1D LiDAR, does not detect that. So this is really something, we can show it again if it was too fast for you. If you again look at the video, so this is a ROS implementation for robotic operating systems, which shows the live sensor data of the TOF devices looking downwards to detect the cliff. So you can see here that whenever the cliff is detected, one of the sensor actually shows a moving structure of the white dots, and this is which gives you the indication that the cliff is detected properly. So, and this form of sensor fusion is really something which is quite beneficial to and can be beneficial to AMR manufacturers or even AMR users. The other use case typically is the obstacle detection. So just here to mention that our sensors are actually completely compatible with the ROS environment. We are currently developing a new ROS wrapper so that robotic manufacturers can directly use our sensor and more or less implement it into their ROS system without any issues and do the sensor fusion right away. So another quite interesting field when it comes to autonomous vehicles are underwater or amphibious drones. So we also see here an increased demand for when it comes to global warming, people need to clean their pools. Therefore, we see here really an increased demand for this kind of vehicles. So what's the drawback when it comes to this kind of application? As you may know, we are using, so most of our sensors are using 850 nanometers, also just conventional, all other conventional types of time of flight or LiDAR devices are usually using IR light for the distance detection. The drawback is that with water, the absorbance coefficient is extremely high for IR light. So you're not able to see more than probably 20, 30 centimeters in water. And that's probably what most of the people would consider as a not usable sensor with such a maximum distance. So therefore, it would be possible to add a green light source, because here, especially when you think of turbid water, so a little bit water with some dirt included, then you see that the green wavelength really has some benefits here, and this is quite easy. So we are also working on a solution where we can integrate also such light sources to also address these kind of markets. If you're interested in such a device, just get in contact with us and then we can talk about that. For the short term, what we supply to our customers is the AFBR-S50 MV68B, which was also introduced previously to you. So it uses 680 nanometers. The advantage here is that really the absorption factor is still a magnitude lower than than with the 800 or IR sources. Therefore, you can reach at least distances of about 2 meters. So what was also mentioned by Stefan before in the overview is safety systems for semi-automated pallet trucks. So all these applications go into the direction of factory automation, more or less, because even if you see here a human person controlling the pallet truck, but on the long run, probably these jobs are also going to be done by fully automated pallet trucks, and therefore you always need a collision avoidance system. And one beneficial system is the one which was realized in a pilot study here together with the Fraunhofer Institute, with a sensor bar, including our sensors, which is assembled on the back of these pallet trucks with an application software which actually includes three distinct distances for 3 distinct actions of the pallet truck, which is either completely do a stop, slowing down the velocity, or when you are still within a safe distance, just move on. So what we are offering for these kind of applications is the AFBR-S50 MV or X85i. Those are the sensors, if you still remember the overview, which are really using all of the 32 pixels and which offer really the biggest field of view. So now let's get into the application field of drones. So what are the typical use cases in drones for these type of sensors? It's actually landing support. They are used for landing support, or again, as collision avoidance system. Specifically, if you think of the field of indoor maintenance system, of an indoor maintenance drone, so especially when it comes to industrial drones, then you cannot use GPS at all anymore, because indoor is usually a GPS denied environment, and therefore you need to have some other alternatives. And those sensors, together with their really tiny small integration size and also their lightweight, they are the perfect match actually for these kind of applications. What we are offering there is the 30 and 50 meter version of the Broadcom TOF-sensors, which can be mounted either on the wings of the drone or just on the bottom side looking downwards for the landing support. And now you will be hopefully able to see the video, our promotion video for the drones, showcasing all the applications. Let me start the video. All right. So that was the that was the small promotion video for the drones, which actually showed all the use cases in a bunch. Regarding outdoor performance, I think this is something which probably we haven't mentioned, or which we haven't emphasized too much up to now, but actually this is one of our key performances actually for our devices. And here you can see a comparison to a competitor part which is on the market. So this is just a comparison at full sunlight at full sunlight exposure of the ground when the part is looking downwards onto three different kind of ground materials. So you have asphalt, you have concrete, and you have grass, and you can see the performance, the performance of the Broadcom on the left column and the competitor part on the right column. And here you can see the noise, which is, or the excess noise of the competitor part, while the Broadcom part is still showing a really smooth measurement here. This is one slide showing already one reference implementation of our sensor. So this is actually a part which can be purchased on the market from the company ARC Electronics. So this part features not only our 30-meter time of flight sensor. I think there will be also the 50-meter version soon available. So it does not only feature this TOF sensor, it also comes with an accelerometer, a gyrometer, then an optical flow sensor, and the TOF for the Z coordinate, the optical flow sensor for the XY coordinate. So all together actually give you really a measure for the absolute velocity. And this is quite a comprehensive part which can be purchased. Going to the next application, this is what was mentioned by Stefan before, to really exploit the unambiguous range of 100 meters for the 680 nanometer part. You can use a retroreflective target, which really gives you almost returns 100% of the energy back to the module, which really lets you exploit the unambiguous range and really let you measure the distances then also up to 100 meters. How can you use that? What's the practical application? It's actually for elevators and for elevator maintenance, for the leveling of an elevator. So the conventional method is here a kind of a mechanical installation. Usually they use magnetic bands, and this could be fully replaced by an optical sensor actually. When it comes to intralogistics, more specifically, there is also eKanban as possible application. It's getting more and more popular really to automate the factory and also automate the fill level of shelves. And this is one possibility is to have these fully electronic featured eKanban shelves, which really measure here, which is displayed on the left and picture, measure the number of packets in one shelf. Another application for factory automation could be with the 32 pixel variant, looking from top to bottom on Euro pellets and really detect the fill level of the Euro pellets. Typically, those are also battery applications, so this can be this is also possible with our sensors. Another application are cameras featuring our TOF devices, mainly for the purpose of the autofocus. So if you think of other solutions, which could be then a typical stereo camera, and if you look at this environment with some monotone ground material, so it's quite hard for stereo cameras to do the job of the distance measurement, and this is actually where customers, and we see a lot of demand for the TOF sensors. Also, the same is for the surveillance cameras, and also when it comes to these retro analog cameras, which become more and more popular, they also obviously need an autofocus, and this is where they are looking for some TOF devices. So this is just another picture to make you aware of the fact when you have a single module, because this is where a lot of vendors always want to have it quite compact, to have everything in one place, which is, of course, from a, let me say, maintenance point of view, quite beneficial. On the other side, from a detection point of view, it's not always beneficial versus a distributed version of the sensors in your system. So this is now a pallet truck moving into a Euro pallet to load the Euro pallet on the pallet truck. So the big advantage here is of having a distributed system that you really can see to the back of the Euro pallet and to do the automated alignment of the forks within the Euro pallet, while with a single camera looking from top to bottom, you don't see really the dimensions here of and the positions of the forklift within the Euro pallets. So that's something really to be mentioned, that one should also think of a distributed sensing system and not having everything on the same place. So this is also where these small, tiny, lightweighted sensors are really beneficial in a system when it comes to system integration. Okay, in the end, let's go quickly. I think we are running out of time a little bit. Let's go quickly to our software. So we are using a dual frequency mode. This enables us really to overcome the ambiguity. So we can measure up to 200 or differentiate between up to 200 meters. We have meanwhile really major binning algorithms which are preset in the software, so you don't have to say, okay, which of the 32 pixels now gives me the correct distance for the closest target. So this is done all by the API and by the algorithms. So we have a really rich API and easy to use API also for conveyor belt applications. You can easily integrate multiple of the devices with a single MCU. So we have an application node here. And we also have, for one of our reference design, which we also will mention, we have now the full 3 kilohertz frame rate support. So in our next upcoming releases, we also we will feature a high precision mode where we even can then measure with sub-millimeter precision. We will have an improved signal quality indicator. This is specifically important for the drone applications. We will have the ROS wrapper included in the new release, and we are also currently working on an full HDR mode, which then enables these devices to be even used as a rotating LiDAR, as a really cheap rotating LiDAR. So just for the software, what is available from Broadcom side? So we have meanwhile a family kit, which is available since beginning of this year. So you have all the 5 sensors which are on the market available in this kit. You have a MCU evaluation board, and you can plug and play this hardware on using your laptop and a USB cable. It comes fully flashed, so you just need to plug and play to your laptop, download the SDK via GitHub. All our software is open source, therefore just go to GitHub, install the GUI on your PC, and then you're ready to go do the first measurements with our sensor. Just mentioning the core of the structure of our software. I think we just skipped that because we're running out of time. Just for resources, we have, of course, data sheets are available. We have plenty of application notes. So for crosstalk compensation, for reference designs, for software porting, and many others. Okay, now let's spend a few minutes on the reference design which we have. So I don't know, Stefan, do you want to take over for the reference design?
Sure, of course. So this is a reference design of our partner Micree. You see here actually a fully equipped microcontroller board, including also our time of flight sensor. You can connect it via UART, CAN, or USB. The 5 volt are supplied externally or via the USB. We have a driver in C featuring also our time of flight sensor API, and we also have a CAN example available online. So you can work with this reference design in combination with our graphical user interface, which you see on the bottom right-hand side. So it's easy to do the first steps with our sensors, but you can also use this reference design for integration in your application. You see here one example, for example, on the top, integrated in a drone. This is also the drone which we were using in the video which you've seen before. Another reference design, or actually also a product from the company Terabi. They are actually also specialized on sensors, on time of flight sensors. You see here housing a module with the MCU integrated, communication via UART. And what's very nice with this product actually is their evaluation report, which can be downloaded on their website, and where they also prove and show. You see here this ambient light of a very bright sunny day, blue sky here, measuring onto a 20-meter target, 50 kilolux ambient light. The target is a great target with 25% remission, and it's no problem actually to achieve this very long range in this environment with this very compact and tiny module of company Terabi. And actually this webinar is sponsored by our partners, distribution partners, EQ Photonics, who is covering actually the German-speaking countries, Germany, Austria, Switzerland, and also the Benelux countries, and also for our English-speaking friends from UK and Ireland, AP Technologies. So thank you for that. And this is actually the end of the presentation, and we will hand over to Keely again for also our Q&A session. Thank you.
Thank you.
Thank you very much. Thanks ever so much, you guys. That was really fascinating. It was so interesting to find out some of the potential applications and use cases there. So yeah, that was great. Thank you. So as the chaps just said, it's time to move on to our Q&A now. We've had quite a few questions come in. If yours doesn't get read out in the time that we have available, please don't worry, because we will collate them and send them to the speakers later to answer. First question, is there any calibration needed when working with these sensors? I'm not sure who'd like to take that one.
Yeah, sure. Let me take this question. So yeah, thanks for the question. This is one of the most common questions actually, because everybody is so much used to when it comes to sensors that you have to do some calibrations in order to make it working in your specific application. Actually, these sensors come fully factory calibrated, and therefore you don't need to do anything. You can start working right away without any calibration needed. There's just one application-specific case where you need a calibration. So when you do a cover glass calibration, of course, you have your own mechanical structure, you have your own cover glass, and this is the case where you actually need to do a calibration. But we have two application notes which are really supporting you here. So we have the cover glass calibration guide, and we have the crosstalk application note, which really supports you here.
Fantastic. Another question, do I need an external MCU? And if so, what are the requirements? I don't know who'd like to field that one.
Yeah, I can also take this one. So in principle, I know due to time constraints, I couldn't get into the details of the software, but maybe you got it in one of the slides, that we don't have a microcontroller included in the devices. So usually one has the freedom actually to use its own microcontroller, which is already embedded in the system. And you can easily use the software, our API, imported to your MCU. So actually the requirement is that you have a 32-bit MCU with a Cortex-M structure. So we have already finished portings for NXP, STM, and Renesas Cortex-M processors. So for the Cortex-M 0 Plus, for a M4, and for a M33 from Renesas. So everything is mentioned in our API reference manual. If you have any further questions here, just contact us. When it comes to requirements for the memory, this is also mentioned in the API reference manual. So usually our API requires 128 kilobytes of flash and roughly 4 kilobytes of RAM.
Excellent, thank you. And also just related, is there a need for a separate MCU for each sensor?
Well, actually not directly. So you can do that for the sake of modularity in a system, but there is absolutely no need. So in principle, you could actually implement as many sensors as you want. But let me say natively, the software supports 4 sensors per MCU. You can even distribute the sensors among different SPI interfaces. So everything is possible. We have actually an application note explaining all the details of the implementation of several sensors onto a single MCU or more MCUs. You can download everything on the Broadcom homepage.
Excellent, thank you. Apologies, I interrupted you there.
No.
Another question, someone has asked the reasoning behind choosing the wavelengths that you did. Would somebody like to field that one?
Yeah, actually, so the reasons, first of all, is also availability of light sources. So simply when you look at the market, there are some specific light sources where you have the freedom to select your suppliers. So this is one reason. Another reason specifically for the 680 nanometer is that we wanted to have a sensor where the sensor spot is visible. So we have a couple of sensor customers. They require to see the spots where we are measuring the distance at. And so this gives you a visual feedback by the eye where the distance is being measured.
Perfect, thank you. And somebody else has asked in terms of the AFBR-50's capacity when facing the sun, can it handle 100K lux directly onto the sensor's face? Would someone like to take that one for us?
Yeah, sure. Of course, at some point, the sensor, as every optical sensor, you will have some saturation effects. But usually what our sensor or the behavior of our sensor is that when it recognizes this kind of saturation effect, that it will just restart the software in a way. So most importantly is when you have a direct sunlight exposure that the sensor doesn't die or doesn't get frozen. And this is what we have implemented in the software. So you have a kind of an algorithm which is actually checking the health status of the sensor, and then when it detects the saturation, it's going to restart the sensor. And usually you don't have this sunlight exposure 100% of the time. So it might be one specific situation where you rotate with your system and you're fully exposed to the sunlight, and then in the next situation you're going out of the sun, and then the sensor continues its work.
Excellent, thank you. We've got time for a couple more. Somebody's asked about the resolution in terms of a little more detail. What do you mean by good resolution, and are you able to provide any numbers at all? Is that something you're able to?
Yeah, so actually we're working, as mentioned in the beginning, with a 32 pixel arrays. We have 4 × 8 APD pixel. This is the resolution by each sensor or for each sensor. And we have actually for all our variants a pixel field of view, which is 1.55 degrees times 1.55 degrees. So this is the resolution you can achieve. But I also would like to add that our sensitivity is so good. So if the object is smaller than this field of view, in most of the cases, you're still able to detect the distance to the object.
Fabulous. And one last question, and this is a great question, thanks for this. How does Broadcom see the time of flight sensor market evolving in the next 1 to 2 years? And how do you think the AFBR-S50 might need to adapt?
This is a very great question. So actually, it's already a very big market, and it's booming a lot. So we see actually also because of the lack of people in warehouses, for example, and the demand of logistics, that more and more companies are really going to fully automized warehouses. And in order to make this work, sensors are really necessary. So we see, especially from this side, a very large growing demand, while also from the drones, we were talking about this, we see actually that there is also some ramping demand for this, but maybe with a little bit of a delay. And especially also when thinking about these autonomous vehicles, navigation inside and also especially outside the warehouses. We see now more and more of these robots also going onto the street, for example, delivery robots, where you have the ambient sunlight. So we see more and more use cases, applications going through all fields of our daily life, so not only of the factories. So this is booming and growing a lot. And actually with our very sensitive and compact sensor solution, I think we are very well positioned in this domain. And we are also looking into a very bright future for this technology. The next steps of our sensors are still open. We were briefly talking about these underwater applications, which is maybe a bit niche, but can be also a very big market from what we know. But we, of course, offering also other sensor modalities, as also said in the beginning, also silicon photomultipliers. We're very well equipped with many different sensor solutions, and we can very quickly react to the needs of the market and offer the right solutions to our customers.
Excellent. Thank you so much. Apologies to anyone who sent questions in that we don't have time to answer. As I say, we'll get these collated and send them to Stefan and Volker to answer later.
Okay.
We have unfortunately run out of time, so that brings us to the end of today's webcast. It will remain on the Electro-Optics website for the next 12 months, and that's at www.electrooptics.com, although obviously the live Q&A won't be functional, so please don't send any questions if you're watching on catch-up. So all that remains for me to do is to thank very much again Stefan and Volker, and to our sponsor Broadcom. Thank you to the Europa Science production team working in the background to make this webcast happen, and thanks to everyone out there who's watched and taken the time to submit questions. Thanks very much. Bye bye.